Hello everyone, I'm Alireza Mahzoun and I'm going to present our paper Polynomial Formal Verification of Prefix Adders. Arithmetic circuits play an important role in many applications, such as signal processing, cryptography, and artificial intelligence. When we talk about arithmetic circuits, we talk about a wide range of different designs, such as adders, subtractors, multipliers, and dividers. Each arithmetic circuit has a unique function. For example, an adder receives two inputs and computes their sum, or a multiplier receives two inputs and computes their product. However, the type and the size of an arithmetic circuit vary based on the application. Type depends on design parameters such as area, speed, power, fanouts, and the number of wiring tracks, and size is determined by the number of input bits and the architecture. Many applications require highly parallel and complex arithmetic circuits with millions of gates. The big size and the high complexity make these circuits error-prone, so proving correctness of them after the design is very important. Nowadays, this becomes possible with the help of formal verification methods. Several formal verification methods have been proposed to verify arithmetic circuits. The methods based on the binary decision diagrams, BDDs, and Boolean satisfiability SAT report very good results for the verification of adder circuits. Binary moment diagrams, star BMDs verify some types of multipliers. Theorem proving and term rewriting techniques are used to prove the correctness of multipliers. And finally, the methods based on the symbolic computer algebra SCA are recently used to verify multipliers and dividers. In this work, we focus on the formal verification of adders using symbolic simulations and the BDDs. Now I explain the formal verification method based on the binary decision diagram. The core idea of the BDD-based verification is using symbolic simulation. In symbolic simulation, we cover the whole input space with a single symbolic test. To do this, first the inputs are encoded as BDDs. Then, starting from primary inputs, BDDs for the outputs of a gate or a building block are computed. This process continues until we reach the primary outputs. Finally, the output BDDs are evaluated to see whether they match the BDDs of the circuit or not. In order to compute the output BDD for the gates or building block of the circuit during symbolic simulation, if then else or ITE operation are used. ITE is widely employed in BDD packages like CUDD as it can compute all logic operations. Here you can see the XOR of two signals based on the ITE operation. The computational complexity of ITE operation can be calculated based on the size of input BDDs as you can see. BDD-based verification is being used to verify adders for a long time. However, the complexity of verifying an adder circuit using BDD has not been yet fully investigated. But why is the complexity of a verification method important? First, knowing about the complexity gives us insight about the scalability of the method. Moreover, it can help us to compare two verification methods and choose the best one for our application. In general, we are interested in formal verification method whose space and time complexities are polynomial, meaning that they have n to the power of m complexity, where n is the number of input bits. As I mentioned, there are very limited works on the polynomial formal verification of adders using BDDs. One of the works is Polyad. Polyad proves that the verification complexity of some adders are polynomial. However, the exact complexity bounds remain unknown. In our work, we extract the exact complexity bounds for three famous prefix adders: serial prefix adder, Latne-Fish adder, and Coggestone adder. Prefix adders have some advantages compared to the other adder architectures. They can be highly parallelized thanks to the prefix operators. Moreover, they can be designed in many different ways in order to meet different design demands, such as low area, low delay, and a small number of wiring tracks. Here you can see the general structure of a prefix adder. The first stage is made of half adders, and the role is to generate and propagate signal. The second stage is PC block, and it generates the carry bits. And finally, we have the third stage, which is only made of XOR gates, and it can generate the final sum bits. The first and third stage of prefix adder are always identical. However, the PC block changes based on the type of the adder. In fact, a tree of prefix operators are used in the PC block to generate the carry bits. Here you can see the prefix operation between two pairs of generate and propagate signals. The goal is to obtain carry bits and then compute the sum bits. A carry bit can be computed using prefix operations, as you can see. Prefix operation is associative. It means that we can do the operation in any desired order or even in parallel. Different orders of the computations usually leads to different prefix adders. We always show the result of prefix operations between consecutive propagate and generate signals as gi to j and pi to j. We call them group generate and group propagate. This equation shows that we can combine group generates and group propagates with the range I to k and k minus 1 to j. We can also see that the ci plus 1 carry is equal to group generate I to 0. We now review the architectures of three important prefix adders. The first adder is serial prefix adder. Serial prefix adder is very simple as all the operations are performed serially. It has in fact the minimum number of operations. However, it is inherently slow. The second adder is Latne-Fisher adder. Latne-Fisher adder has the smallest delay and also few wiring tracks. However, the number of fanouts in each node is high. The third adder is Kaggle-Stone adder. It has the smallest delay similar to the Latne-Fisher adder. Each node also has bounded number of fanouts. However, it consists of large number of prefix operations. In order to calculate the verification complexity, we start with the first stage of a prefix adder. In this stage, we have half adders that generate, propagate, and generate signals in parallel. So we can translate the function of a half adder into two ITU operations. We showed in the previous slides that the complexity of an ITU operation is equal to the multiplication of the input BDD sizes. Thus, we can get the complexity for a single half adder. As there are n adders in the first stage, the complexity of the first stage equals 36n. Now we calculate the complexity for the third stage. In this stage, we have the XOR operations between group generate gi-1 to 0 and propagate signal pi. We can translate it easily to an ITU operation. Based on the complexity of the ITU operations, we can get the complexity of computing final sum bit Si. This complexity is dependent on the size of the group generate gi-1 to 0, or equivalently, the Ci carry. It has been proven before that the size of the Ci carry is bounded by 3 times I plus 1. Thus, the complexity of a single XOR operation is obtained by substituting carry sizes. Finally, we add up all the XOR complexities to get the complexity of the third stage. We have shown that the prefix operation between the group generate and group propagate can be performed as you see. We can convert this prefix operation into ITU operations. And subsequently, based on the complexity of the ITE, we can get the complexity of a prefix operation. The complexity of computing group generate and group propagate are dependent on the BDD sizes of group generate and group propagate. We have proven in the paper that the BDD sizes of group propagate m to n and group generate m to n are bounded by 3 times m minus n plus 5 and 3 times m minus n plus 4 respectively. You can find the details of the proof in the paper. Finally, we can get the complexity of the group propagate and group generate. We call them CG and CP. Finally, we add up the two complexities to get the prefix operation complexity C. C is a function that receives I minus k and k minus j as inputs and computes the complexity. We now calculate the complexity of the PC block, and we start with the serial prefix adder. In a serial prefix adder, the prefix operator in the T position performs the following operation. In the previous slide, we have calculated the complexity of a prefix operation. So based on that, we can obtain the complexity of the prefix operator in the T position. In a serial prefix adder, we don't use the group propagate signals. Thus, we can exclude them from the calculations. In other words, the complexity of computing group propagate equals 0. Finally, we can get the complexity for a single prefix operator. By adding up all the operators' complexities, we can obtain the complexity of a serial prefix adder PC block. The order of the complexity is O(n) to the power of 2. It means that it has quadratic time complexity. The complexity of verifying the whole adder is also quadratic, as adding up the complexities of first and third stages does not change the order. We continue with the Latne-Fisher adder. The PC block of a Latne-Fisher adder has a tree structure consisting of many prefix operations. We can calculate the complexity of each prefix operator based on the C function with the two inputs, as you can see in the figure. The depth or number of rows in a Latne-Fisher adder is equal to log 2n, and the number of nodes or prefix operators is in each row equals n divided by 2. We put the nodes with the same fannings in the same groups. Thus, we have 2 to the power of log 2 n divided by 2 minus L groups in each row and 2 to the power of L nodes in each group. We first calculate the complexity of each group by adding up the complexity of each node in the group. And then we calculate the complexity of each row. Finally, we can get the complexity of the whole PC block by adding up the complexity of each row. The order of the complexity is n to the power of 4. It means that it has quartic time complexity. The next prefix adder is the Cogestone adder. We can again calculate the complexity of each node based on the C function. In a Cogestone adder, the depth is equal to log 2n and the number of nodes in each row equals n minus 2 to the power of L. We divide the nodes in each row into two groups, where in one of them all the nodes have the same complexity. In the figure, you can see the groups with the green and the red colors. Number of nodes in the first and second group equals n minus 2 to the power of L plus 1 and 2 to the power of L minus 1. We first calculate the complexity of each group and then we add them up to get the complexity of the PC block. The order of the complexity is n to the power of 4. It means that the verification has quadratic time complexity. We have also done some experiments to confirm the theoretical results. We have implemented the BDD-based verification method in C++, and we have run it for 3 prefix adders with different sizes. Then we fitted a function to their runtimes. As you can see, the experimental results confirm that serial prefix adder has quadratic time complexity. It shows that the Latne-Fisher adder also has quadratic time complexity. It might seem in contradict with the quadratic time complexity that we proved in theory. However, the theoretical results are always the upper bounds or worst cases. Therefore, if the order of complexity in practice is equal or smaller than the order of complexity in theory, it still confirms the theoretical calculations. Finally, experimental results confirm that the Cogestone adder has quadratic time complexity. In this work, we calculated the verification complexity bounds for 3 prefix adders: serial prefix adder, Latne-Fisher adder, and Cogestone adder. We proved that polynomial formal verification is possible for these 3 adders. We also did some experiments to confirm the calculated complexity bounds in practice. In future, we plan to calculate the complexity bounds for more adder architectures. We also want to investigate the complexity of other verification methods. Thank you for your attention.